Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2024 VCE sample chemistry paper, part 2 of the multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. Guys, this is just a disclaimer, these are my suggested solutions. Please let me know if you see any mistakes and I'll have a look at them. And yeah guys, let's smash through this paper. Question 17. The structure below is lignin, a compound commonly found in the leaves of some Australian native trees. What is the most suitable solvent to extract lignin from leaves? Ooh, alright. So this is actually new in the study design. It's actually called solvent extraction. So, how does solvent extraction work? Well, I'll just explain what it is, basically, and how we can determine what solvent we should use to get that lignin. Okay, so what solvent extraction looks like is basically you have like a funnel, basically. Like a normal funnel here. You have a funnel, something like this. Say this here is where the tap is. All right, something like this. And so let's say you have lignin. Let's say you have leaves of lignin, and basically, let's make the green ones, these green molecules, lignin, basically. So these green molecules are lignin. And these are the ones that we extract. Now, if you take a leaf, of course, the leaf just, doesn't purely have lignin. It actually has impurities. And let's make those impurities red. So make those impurities red. Something like that. Not like that. Let's make these impurities red. Now, what solvent extraction does is we want to get rid of those impurities and we want to get the lignin itself. Now, to use solvent extraction, it's all about is the molecule that you want to get, is it polar or non-polar? Now, let's look at the structure of lignin. There's no oxygens. There's no actual, it's just all carbons and hydrogens, meaning that it's very, very non-polar. So, lignin is very non-polar. So, I'm going to make those green ones. So, green are basically our lignin. Green. So, let me write that. Lignin are basically our green circles, like those green circles that we see right over here. And we know lignin is very non-polar. So basically how solvent extraction works is basically if you want to extract lignin, which is non-polar, you want to use a solvent that is also non-polar. So what we're going to do is I'm going to use a solvent. So I'm going to call this a solvent that is also non-polar. Now, of course, the red ones here, these red circles are basically impurities. And these impurities, we consider them as basically polar. We consider them as basically polar. And so, yeah, to extract lignin, we have to use a solvent that is non-polar. Let's think about it. So if we use, of course, a non-polar solvent, so let's put it something like this. If we use a non-polar solvent, so the solvent here, all around it is non-polar. Great. So remember, it's very attracted, that solvent is very attracted to that lignin, those green molecules. Because remember, non-polar likes non-polar. So yeah. So what we also do is we also basically put what we say is basically another solvent. And it's also polar. We use a solvent that's basically lower in density and we basically put it on top. And that basically solvent is, we use a less density, so it's actually on top of our, tube. And basically, it has to be polar. And guess what we just do? We basically shake it. We shake this system. We shake it, and guess what happens? This is what actually happens. So if we shake it, this is what really happens. Because remember, the solvent that is polar, it will take all those impurities, not all of them, of course, but it will, because it likes polar, it's going to try to get those impurities out. So the impurities, those red, are going to come on top. So man, all these reds are going to be here now. While, of course, the lignin that we want to get, it's going to be kept within the solvent that is non-polar. That solvent right here, you can see. And so when we open this funnel, we actually just release our lignin molecules. Now, of course, this is not 100% efficient. You have to kind of do it many times. So it is, that's how you do it. So overall, what is the most suitable solvent to extract lignin from leaves? Easily, you use a solvent that is also what we want to extract. Remember, what we want to extract, we use the same polarity as it. So if we want to extract lignin, which is non-polar, we want to use a solvent that is also non-polar. So which one of these are non-polar, like out of these ones here? So water is polar, ethanol is polar, hexane is great. Hexane is actually non-polar, propanol, polar. So it's actually C. That is your answer. Beautiful. 18. Enzymes commonly start to denature when temperatures reach 50 degrees or more. Which structural changes are most likely to occur in an enzyme if it is placed in a solution of 50 degrees? So remember, denaturing occurs only in the secondary. Secondary, where basically hydrogen bonding is broken. So hydrogen bonding. Also tertiary, where you remember tertiary has a lot of bonding. It has ionic bonding, dispersion forces, hydrogen forces, sulfur. It has a lot. Disulfide bondage, all these. So many intermolecular forces. These are broken out. And also the quaternary structure. That basically has the same intermolecular forces as the tertiary. So many intermolecular forces. Okay, so let's see. So basically, yeah, when you denature it, remember, the primary structure is not affected. You know those peptide bondage? They're not affected. It's only the secondary, tertiary, and quaternary, those intermolecular forces that are absolutely getting broken. So let's have a look at this. Peptide links in the primary structure will be broken. Rubbish. Like we said, primary structure, those peptide linkage will not be broken. So remember, when you have a peptide, the structure like this. Come on, if you have a peptide like this, in its what we call in its like, what's happening with me? What am I saying? In its primary structure. So if I just nicely draw like this, if you see this peptide, you can see all those linkages here. That's linking these are peptide linkages. And that's the primary structure. So those are not broken. Remember, those are not the ones that are broken. So when they never broken. When they denature, they actually don't get broken. They're very strong. They have very strong covalent bonding. So no, that's not correct. And remember what we said, only quaternary, tertiary, and secondary are broken in this in denaturing, not the primary. Next one. Covalent bonds in the secondary structure will be broken. Rubbish. I mean, so in the secondary structure, remember what happens in the secondary structure? There's hydrogen bonding. So let's say you have this here. What happens is you get hydrogen bonding. So it kind of bends. It's what folds it. It's those hydrogen bonding. The tertiary structure is when the primary structure folds. So imagine this here. Oops. When this structure is basically folding. Like this. See, it's folding like that. Something like that. You can see that it's kind of folding, and it's just due to the fact that there's hydrogen bondings. These hydrogen bondings are occurring. And that's what basically bends it. Remember, secondary structure all is about the hydrogen bonding. And that's what breaks down. And when it denatures, those hydrogen bonds are broken down. Not those covalent bonds, those peptide bonds. It's only the hydrogen bonds that are broken down. Covalent bonds in the secondary, rubbish. Like we said, only the hydrogen bonds are broken down. C, intermolecular forces in the tertiary structure will be destroyed. Absolutely. That's what we said. Tertiary structure, those intermolecular forces, those disulfide bonds, those dispersion forces, those dipole to dipole, hydrogen bonding, many of ionic bonding, all those are breaking down. So this one looks great. Disulfide links present in the structure will be broken. Now, yes, the disulfides are in the tertiary and quaternary. What about the secondary? Or what about, it's not being very specific, because it's like saying only disulfide linkages will be broken. No, hydrogen bonds will be broken, ionic bonds, all the other ones, dispersion forces. So it's not being very specific, so choose C as your answer. That's the best out of all of them. Easy. Question 19. Let's have a look at this. When a single cysteine residue is present in the primary structure of a protein, so in the primary structure, remember the primary structure is just peptide linkages. So like this, you have peptide linkages, like that. Like what we drew, straight peptide linkages. Something like this. Let me just nicely draw this. So, there it is. Something like that. All right. So when a cysteine residue is present in the primary structure of a protein, which of the following shows the strongest types of bondings that can form between the R groups of the cysteine residue and any other acid R group along this chain? Ooh. All right, this is a great question. So let's think about it. There's only one cysteine. So single says. So basically, let's say this is here is the cysteine molecule. And remember, the cysteine actually is very important. It actually has it actually creates disulfide bonds if it also has another cysteine molecule. Remember, disulfide bond, di comes from the word two, so it needs to have two. But there's not going to be disulfide bonds in this case because there's only one single cysteine, and the other ones have to be different because it says a single cysteine residue is present in this primary structure of this protein. There's only one of them. And the other ones are going to probably be other stuff. So you can't form disulfide bonds. Remember, disulfide bonds are one of the strongest because they actually are covalent bonding. Yeah. Which following shows the strongest type of that can form between the R groups. So absolutely take D off. Covalent bonding. It's not going to be those. So yeah, covalent bonding are not, because you need to form, if it said like two cysteine residues or like, because it says single, there's only one, so it doesn't work. Ionic, remember, ionic only works if you have a charge, if it's charged. No, hell no. Like the cysteine molecule is not charged. You can even realize this. Oh yeah, by the way, if you're wondering where there is cysteine, it's actually in your formula sheet. If you go to your amino acids, here it is. Cysteine. Here it is. Cysteine's here. It has this SH group here. This it can form disulfide bonds. So yeah, it's not even charged. So remember, ionic bonding occurs when there's charged molecules, and so that also doesn't work. Dipole to dipole attraction. Yeah, absolutely. Like, okay, dispersion forces. Every molecule has dispersion force. That's the weakest. We want the strongest. It has to be B. Now, yes, it can actually form dipole to dipole because remember, as sulfur is actually on the right-hand side and it's actually here. It's a very, what we call electronegative. So it basically creates this like this negative partial charge, and the hydrogen will become this partial charge. So yes, dipole to dipole attraction is actually able to form. And that's like the strongest one that it's able for this molecule to happen. So I just want to double check. I think it was sulfur. Sulfur, if you look at it in your... There it is. So you can see that it's actually a strong... it's very strongly electronegative. You can see oxygen strongly, fluorine, chlorine is actually on the top right. Top right, basically. The more it's closer to the top right, the more stronger it's electronegative. So yeah. So I would say 19B in that case. Beautiful. So that looks good. Next question. 20. There are many chemical pathways in which 2-chlorohexane can be made. So let's just draw the structure of 2-chlorohexane first. So chlorohexane, so it's a C. Just want to C. There's 6. 1, 2, 3, 4, 5, 6. And it's 2, means 1, 2, it has a chlorine here. And the other ones are all basically hydrogens. Now, I can't be bothered drawing those hydrogens, so I'm just going to draw these lines here, meaning that these are hydrogen. Whichever following is a step that could be used to make that 2-chlorohexane. So we want to make that 2-chlorohexane. So let's look at the first one. Reacting chlorine gas with 1 hexene. So let's draw hexene. So hexene is 1. So it has a double bond at 1. 1, 2, 3, 4, 5, 6. Looks like this. And if you react 2 chlorine molecules, so chlorine gas is 2 chlorine molecules. This is going to be an addition reaction where basically chlorine will break this bondage here. There'll be a chlorine here. And there'll also be a chlorine on this over here. And so those hydrogens will be normal. So, but there's 2 chlorines. We only want 1 chlorine, so that's rubbish. He is wrong. Let's check the next one. Reacting chlorine gas with 2 hexene. Ooh, so 1, 2, so there'll be 2 here. Double bond. 3, 4, 5, 6. And it'll look like this. And you're reacting with chlorine gas again. So again, it's going to be an addition reaction where chlorine will break this double bond. And chlorine will be here, and a chlorine will be here. So again, we have 2 chlorines, big problem. Nope, not that one. What about C? Reacting hydrogen chloride in the presence of UV light with hexane. Let's have a try at this. So if you draw hexane, 1, 2, 3, 4, 5, 6. This is hexane. And if you put, hydrogen chloride, which is hydrochloride. Now, okay, this is going to be a substitution reaction where, yes, chlorine could be here, but there's a big problem. Where the hell is... now you've got this... Like, where is this... Because we want the chlorine to be, like, on top here. We want it in the second carbon. you don't know where, you don't know. There's so many possibilities. The chlorine could be here when you go through the substitution reaction, when you give it UV light, or it could be here, or it could be here, or it could be, there's so many possibilities. So that's not true. This is not the best actual way you would, try to make that 2-chlorohexane. Next one. Reacting hydrogen chloride in the presence of a catalyst with 1-hexene. So this basically, 3, 4, 5, 6. Okay. And so you're reacting with hydrogen chloride. So hydrogen chloride looks like that. Now, when you're reacting with hydrogen chloride, yes. So beautiful. It's going to go through an addition reaction. Now, there's two possibilities. You can have the chlorine hitting here, breaking this bondage, and the hydrogen goes here. So like a normal hydrogen, it'll look like this. And that's what we want. Don't we want this one? Yes, we do. Or it could be the opposite way. So if I just take this, it could be that this chlorine actually gets put over here. Something right here on that carbon there. And that's not what we want. So because there are two products, it's better than having C as your answer, because remember, C gave us so many probabilities. So absolutely D would be the best in this case. Now, if you don't know, this is not in the study design. Of course, these are the products, but the major product is going to be this one, which is what we want. It's actually going to be the major. So if you actually did this reaction in real life, you'll actually get more of this compared to this rubbish over here. And that's what we want. Don't we want more of this? That's what our goal is, this over here. And this is not in the studies. You learn it at uni. It's called, I don't know, the word Markov thing. What it is, it's basically the major product is always going to form when, this is what happens. This is how it basically I'm just going to show you a quick way to understand it. What happens is, which one of the following would be like the major one? Would it be this one or this one? How would you know? Well, this is how you would actually know. When you were doing that 1-hexene, let's draw that 1-hexene. So it was 1, 2, 3, 4, 5, 6. There was a double bond here. Now let's have a look at it. What the molecule does is, that how there's a hydrogen and there's a chlorine. It wants to maximize its hydrogens. Like for example, if I put this chlorine here, the hydrogen will go here. Now look at this, carbon. It has 3 hydrogens. So the carbon is maximized. It has the most hydrogens that it can carry. But look at the other case. If we did this to it, if I put that hydrogen here, and then I put that chlorine here, look at this. We only get 2 hydrogens here. So it's not maximized. What the overall, and a molecule wants is to get those. It wants to maximize its hydrogens. So this is not the most major product you would want. So the major product would be when the chlorine is here. Why? Because you actually get more hydrogens here. You see, these hydrogens are in this carbon. Because if you put that chlorine there, if this hydrogen was here, and if you put this chlorine here, you only get, what's the maximum? You get 2 here, and you get 2 here. The other one had 3, so absolutely. So the major product is, if we were doing the reaction, it's actually what we want. It is D as your answer. Absolutely D. Beautiful. Now, you don't need to know that. I don't think it's in the study design, but yeah, it would be if I was doing the exam, D would be the most suitable answer compared to C. So absolutely choose that as your answer. I hope that makes sense. All right. Let's use a different color now. 21. Carbon NMR spectrum of a naturally occurring 2 amino acids shown. So we can see that there's 3 carbon environments. This is good. Which of the following could be the 2 amino acids represented in the spectrum? All right, let's check. So because there's 3 carbon environments, let's check which one of the following has, we'll look at it, which ones have the 3 carbon environments, and we'll go from there. So let's look at serine. Serine, I don't even know how to say that. Let's look at serine, which is here. Right over here. How many carbon environments does this one have? Okay, we get 1 from here. We got 1 here, and we got here. So there's actually 3 carbon environments. That's great. And that's why there's 3 picks. It could be that one. What about valine? Valine, where is that? It's over here. So valine has 1 here, 1 here, also another one here. So that's 3. But there's also 4 because of symmetry. These 2 are symmetrical. This is considered as 4. There's actually 4, which is a problem. We don't want 4. There's only 3 picks. So that's 1, 2, 3, 4. Yeah, that's not B because there's 4. Is it alanine? So let's have a look at alanine. Alanine looks like that. So we get 1, 2, 3. Yep, it could be alanine. It has actually 3. What about glycine? So glycine looks like this. Glycine only has 2. 1, 2. So not D, because there's 2. There's supposed to be 3. Okay, now you're probably like, okay, so we got this A and C. Luckily, it's a 50-50. Now let's check. What's the difference between serine and alanine? And that's what we're going to basically compare with the graph that we have here. So serine, alanine, where's alanine first? Alanine is just like a normal thing. Like it doesn't have any functional groups. It's just a CO. The main thing is what's different is just it has a CH3 here. Whereas serine, what does it have? It has an OH. Jackpot. An OH group. This is important. So that's what it has. All right. So basically what do we know? We know this one has an OH. The most importantly, it has OH. The other one had a CH3, I think. So alanine had a CH3, if I'm not mistaken. Yeah, it had a CH3. So what I'm going to do is go down to my carbon NMR data and let's compare them. So serine is an OH. Where is OH? This is where the OH is. You can see that. It actually occurs at 50 to 90. 50 to 90. Is there peaks at 50 to 90? So 50 is here. 90 is here. Yeah, we got 2 peaks. I mean, yeah, it could be, these. So that's okay. It could be serine. What about alanine? The main thing about alanine, it has a CH3. So this one here. It occurs at 8 to 25. Where's 825? 825 is around, let's say here to 25. It's around here. No, there's no peaks in that place. It can be actually, in other words, it can be alanine. It has to be serine. So choose A. It doesn't have that CH3. Yeah, there should be a peak here, but there isn't. So beautiful. All right, that's not bad. Okay, next question. A mixture of propane 1-ol, octane, hex 1-ol, octane 1-ol, and this was passed through a HPLC column that had a non-polar stationary phase and a polar mobile phase. The chromatograph obtained is shown. Okay. Peak 5 in the chromatogram is most likely to be what? All right. Easy. So what I'm going to do here is I'm going to just draw like a nice, what do we call it? Like a nice paper chromatography to kind of represent this. What does this represent? So think of it like this. Basically, these here, the time is what we call is retention time. It's the time it takes for, like, think of it like this. Well, what is the stationary phase? It's non-polar. This is made from non-polar. Non-polar. So think of it like this. Basically, can you see number 1, how it basically has the lowest retention time? Basically, what it means is, imagine it's basically placed here. It quickly falls off. It quickly basically falls off because it's the time it takes to come out of the chromatography. So like, for example, if it's here, it will take around, let's say, I don't know, what is it, 5, 6, 7, 8. It will take basically 8 minutes to start from here and go down and fall off. Basically, that's what it means. Whereas 5, which is the longest one, it means it takes so long to come down until it falls. It takes actually like 24 minutes. And why does it take so long? That's the question. It's because, remember, if the stationary phase is non-polar, this means because this is 5 here. I mean, that's the 5 one. That's the one that's the longest. It means that it's strongly bonded to that stationary phase, meaning that it has to be strongly non-polar too. Remember, non-polar loves non-polar. It's very bonded to it. So it takes it takes a very long time to come out. So that means that because, that peak 5, which is the longest retention time, it means it's very attracted to that stationary phase, which is non-polar. So it has to be the one that's the most non-polar compared to the other molecules. So octane, yep, that's non-polar. Octane 1-ol, it has OH, so that's going to create hydrogen bonding. Nope. Again, the same with this. This is polar. 1-chloropentane, this is dipole to dipole, so nope. That still creates polarity. So it's only A. A is actually just basically the most non-polar out of all of them. So it has to be 22A. Beautiful. 23. Let's have a look at this one. In which section of the VCE chemistry process should a student identify the limitations in their data and method? All right, so introduction. No, introductions, you just talk about the theory and stuff. You don't introduce limitations. You haven't even done anything. The introduction is basically, explaining the theory, why this experiment's important, blah, blah, blah. You don't, no limitations, that one. B, method, no. So in the method, you basically just talked about the steps that you're doing. like what you're gonna do in the experiment, like yeah, like the safety measure. I don't know. What do we call it? The steps that which you'll be taking. Discussion. Yeah, discussion. Like if you do a poster, what you're gonna see is like there's gonna be questions like, what are the limitations, or what could have been this. So in the discussion you talk about like the results, your limitations and stuff. Yeah, discussion is one of the best places where you would put your limitations. Conclusion, rubbish. Be careful. Conclusion, you don't add up anything new. The conclusion is the most basic and nicest thing you write. You basically just sum up everything. You'd be like, okay, if say you were looking at how temperature affects rate of reaction, you just say increasing temperature increases the rate of reaction. That's all you have to say. It's very simple, like to the point. So you don't add up anything new. By the way, in conclusion, you don't add up anything new. So in the C, I would say C, discussion, is where you basically put the limitations, of course. 24, let's have a look at this. Ideally, before scientists can publish experimental results, the research that has been undertaken should undergo a process in which the experiment is repeated by an independent group of scientists. This process would verify it's easy. Reproducibility of the experiment. Yeah, reproducibility. Is the results that you got reproducible? So let's say, for example, you did the experiment and you got these certain results. And now I'm going to do them in my lab. And if I get the same results as you, these results are called reproducible. Other scientists can use them and they do your experiment and hence get reproducible results. So yeah, absolutely. So that worked. Repeatability of the experiment. No. Repeatability. Be careful with the word repeatability. Repeatability is not it's not independent groups of scientists that do it. You're doing it yourself. For example, if I did the experiment once and I'm going to do it like 10 more times just to get the same results, that's called repeatability. Seeing if the results are going to be the same. It doesn't mean that another group of scientists are going to do it and get the same result. It's myself that I'm doing it. Hope that makes sense. Yeah. So not absolutely that. See, accuracy of the experiment. Rubbish. What does accuracy got to do? Remember, accuracy is like how close is your values, your results to the true value. And that has nothing got to do with like, doing with scientists, an independent group doing it to verify. Validity of the experiment, nothing to do with validity. Also, remember, validity is basically like how valid the experiment. Are you following your aim? Are you answering your aim and stuff? That what does like other scientists have to do with that? Nothing. So it's A. This is the actual definition. This is a textbook definition what reproducibility is. It's basically other scientists. If another person did it, is he going to get the same results? And hence it is reproducible. So make sure please to know these. Reproducibility, repeatability, all the other stuff. Yeah. So you need to know those definitions. 25, the following is an extract from a safety data sheet from a chemical that Suresh considered using as an organic reagent in his student-designed scientific investigation. So it's hazards identification. So classification of substance or mixture, classifications according to the regulation. Let's have a look at these. Acute toxicity oral. I think this just, the word oral comes from, so a toxicity oral meaning that like if you use that thing, if you swallow it, orally means you put it in your mouth. So this means that like if it becomes toxic. You're toxic if eating it, like in digesting it accidentally, like if it's in your mouth and you digest it, it can basically you can become toxic. Like you feel sick of it. You'll get sick. What about the next one? Acute toxicity inhalation. Even inhalation, so you can't even breathe it. So breathing is so we can't breathe it. The chemical. Dermal comes from the word skin. So dermatologist, all that stuff. Dermal means skin. So probably you can't even touch it with your skin. So irritation, skin irritation probably. So skin irritation. Skin sensitization, I don't know what that means. Basically the same, I think. Carcinogenicity, basically that means you can get easily cancer. Like it can give you tumors and stuff. So cancer. Damn, what kind of substance are they using? It has all these rubbish. Specific target organs toxicity. So basically organ toxicity is a problem, your organs. Long-term chronic aquatic hazard, big problem. So like, for example, if it's not put properly, like say a student washed it through the sink and it goes towards like, let's say to the ocean or something, it's very bad for the animals. It's very toxic to those animals. So that's a problem. Hazardous to the ozone layer. Also, that's a problem. I'll be honest with you, this chemical is rubbish. Like, why? Yeah, It's very dangerous. Like it has everything that's worse. You can't even touch it. You can't even feel it. You can't even smell it. You can't even do anything with it. It's and it gives you cancer. Like it's just one of the dangerous things that it should be taken care of by, I think, university students, like those that are actually proper. Yeah. According to the information in the safety data sheet above, which of the following statement is best or recommendations for the use of this chemical in a secondary school laboratory? Okay, no. In a secondary school laboratory, this should never be trusted. You don't use a chemical like this. This chemical has so many flaws that not even students are perfect at using it. This has to be done, like, these kind of chemicals and stuff probably are good for uni students. They are more, but like, let's say it's very dangerous for students. I mean, it's too dangerous. It has all the problems with it. Like, I'm telling you, some students would accidentally put it in the sink and like they'll wash it away, and that goes killing the aquatic, or they breathe it. I mean, you need gas masks, you need fume boards, you need orally. What about orally? Like, what about inhaling it? So you can't even touch it. You need actual proper. So it's just for secondary school students. I think it's it should never be used, never be touched by secondary school students. So too dangerous. Has too many flaws than positives. That's the truth. According to the information, okay, it should be safe if only small quantities. Rubbish. No. Still not safe. Even in small quantities, probably is even more still dangerous. It should be safe if it's only used in a fume cupboard. Rubbish. Yeah, fume cupboard. Well, let's say you minimize the breathing. But you've got skin irritation, which is a problem. Eating. Eating. No one gets eating, but like organ toxicity, cancer, all these other stuff are even worse. It is not safe to use, all due to the long-term risks. Absolutely, that is perfect. Never use for secondary students. Shouldn't be used. Let's have a look at that. It should be safe if the waste are washed down the sink with a lot of water. Rubbish! You don't wash it down the water because it has aquatic hazards. It basically affects animals and all that stuff. So it's only C, I would say. Yeah, absolutely C would be the best. This is too dangerous. It has more flaws than good stuff about it. So yeah. 26. A student Ruby investigated how the total surface area of a piece of marble. So this affects its rate of reaction with hydrochloric acid. So we're given the molar mass of the marble. So the equation for this reaction is shown. So when we react it, we form water and CO2. And also that. Okay, Ruby conducted 2 experiments. Experiment 1 and experiment 2. In each experiment, she used a different shaped piece of marble, with each piece having a mass of this. The marble used in experiment in experiment 2 had a greater total surface area than the marble used in 1. Perfect. So you should already realize that, remember, having a greater surface area, what happens? The rate of reaction is increased. So I would suggest straight away, without even looking at the results, we know experiment 2 would probably have like a greater rate of reaction. In each experiment, Ruby added 100 milliliters of 1 mole of hydrochloric acid to the marble and collected a gas that evolved in the gas syringe. She measured the volume of the gas at 20-second intervals. Ruby used the data she generated to plot the graph here. Okay. Makes sense. You can see that in experiment 2, it occurs quicker. It reaches equilibrium much quicker. So it's reaching equilibrium at 100, whereas the other one reaches equilibrium at experiment 1, 160. So straight away, we know that increasing the rate of reaction, increasing the surface area increases the rate of reaction. Which of the following is a valid conclusion that Ruby could draw from the graph? So conclusion, like we said, be careful the words conclusion. It's so easy. Do not misunderstand it. Remember, what were we measuring? What are we measuring? So investigate how the total surface, this is what we're measuring. How the total surface area of the marble affects the rate of reaction with hydrochloric acid. Done. How would you write it? You just be like, looking at this result, we should know that increasing the surface area of the piece of marble, you just say this. Increasing the surface area of the piece of marble increases the rate of reaction with hydrochloric acid. That's a valid conclusion. So basic. You compared them, you said the results. That's it. Let's have a look at the first one. Both reactions have reached equilibrium at 160. Rubbish. 160 is reached by experiment 1. By experiment 2 reaches it quicker at 100 seconds, we see here. In each experiment, both reactors have been totally consumed at 160 seconds. I don't know. I don't think so. This would happen. Now, to check that, you would have to check which one's in excess and which one's in limiting. So if there's excess, it means they're not basically consumed. There's always excess. So out of these two reactants, which one's going to be in excess and which one's going to be on limiting? Remember, your limiting one's going to be used up. Your excess is going to be there's going to be excess of it. It's not going to be all used up. So if there's excess, then it's not all used up, so B would be wrong. I think the way that's why they gave us calculations and stuff. So let's do that. First, let's calculate the mole of CaCO3. Remember, it's the mass over molar mass. So what's our mass? We're using 0.34 over, what's our molar mass? So 100.1. That gives me 0.0034 basically mole. What about the mole of HCl? It's so we're using 1 mole of HCl per 100 milliliters. So remember how to get that? Remember N equals the mole equals, sorry. So mole is equal to the volume times your concentration. So that will be 1, which is 1 mole, times 100 milliseconds. So 100 times 10 to the negative 3. Make sure it's in liters. So that's going to give me 100 times 10 to the negative 3. That's 0.1. 0.1 mole. Done. Now we've got the both reactant moles. We can now do our check which one's our limiting and excess. So this is new. It's not new in the study design. It is taught in year 11, but now we've basically put this in this study design. So let's check. How do you check? Well, we just pick one random. Like I'm going to pick this CaCO3. So I'm going to pick that one up first. COO34. And I'm going to use this here. And I'm going to try to calculate the mole of hydrochloric acid. Now we know it's this one, but we're going to try to calculate it and see. So we're using this, and I'm going to try to calculate the mole of hydrochloric acid. Now it's a 2-to-1 ratio, so basically multiplied by 2. So it's basically like 0.0068 mole. Now, are these the same? No, they're not. This one is much more. Look out. So this one here is so much more than this, meaning that this hydrochloric acid is in excess because it's more than what we got. It's much more. So this hydrochloric acid is in excess. And this one here must be our limiting. This lets me know that your CaCO3, your marble will, be used all up, but your hydrochloric acid will be left, some will be left behind. So yeah, they're not all used up after all. The greater the total surface area of the marble, the greater the rate of reaction. Like we said, let me just double check. So we were comparing the total surface area of the piece of marble, how it affects the rate of reaction. The greater the total surface, the greater the... Yep, that's perfect. What we said, the greater the total surface area of the marble, the greater this rate of reaction. That looks perfect. What about D? The greater the total surface area of the marble, the greater the amount of CO2 produced. That's not what we're measuring. Remember, just be careful of that. So I want to say D is right. C is more right because remember, this is what we're overall trying to measure. That's what we were trying to measure. What was our independent variable and dependent variable? These stuff here is just used as a, help us to support our hypothesis. So the greater the total surface area of the marble, the greater the amount of CO2 produced. Yeah. Now that is correct. You would not greater. I don't think. No. It wouldn't be the greater amount of CO2 produced. Also, I think they're produced at the same time. Like no, you can see that when they reach equilibrium, they basically are producing the same amount. So no, so it has to be C, and C is the best one actually. Yeah. I hope that makes sense. Yep. 27 below is an image of a reading of an ammeter used by student Lean during the electrolysis of a solution. Lean connected the ammeter so that the lower scale, the 0 to 5 scale was used to measure the current. So not the upscale, let me use a red color so to see this. Not this scale, the top ones, the bottom ones, so these ones here. This is a very old one, wow. We actually use it in electronics. If you do systems engineering or you did electronics in year 10, you would use this. This is called an ammeter. It measures the current. This is quite old. We don't use that anymore. We use basically what we call is a ammeter. Ammeter meaning that it measures amps, which is current. So yeah, we're going to be using that scale here. This is the bottom one. Which of the following is correct regarding the resolution value for the data being generated by this instrument and the corrected value of the current that Lean should be recorded? Easily. So resolution is basically part of a new study design. It's one of the new points. This is quite easy. If you actually do physics, you are in luck because there's so many questions like this where they give you, this is actually quite new in this like I've never seen a question in chemistry that they do this. They normally do it for physics. So what is resolution? So basically think of resolution in small increment. For example, if you remember we're looking at the bottom ones. Do not look at the top ones. So Can you see how this is the smallest increment? These are always the smallest increments. Can you see? These are the most smallest measured increments. What is that increment? That's what we need to calculate. Well, this increment here, that's our resolution. You know how that's 1? So this one has to be 0.5. Then this one has to be 0.1. So your smallest increment is actually 0.1. Your resolution value has to be 0.1. So it's not C and D. Now, what's the correct value? Well, let's have a look at it. So it's 1. You can see it's 1 to 1.1. So it's 1.5, like 105 or something. So B looks right. This one's rubbish. Look at this one. They're trying to trick you here. Be careful. They're trying to use the top one here. Use the bottom one. They told you to use the lower scale, not the top scale. So just be careful with the wording here. Easy. Nice question. Question 28. Let's have a look at this. Vitamin C can be analyzed using a redox titration where DCB solution is used as a suitable titrant. A volumetric analysis of vitamin C drink was performed by a VCE chemistry class. In this titration, 20 milliliters of allocates of vitamin C drink were titrated against a standard DCB solution. Okay, 28. Another student, Diego, consistently found that he was getting a high results from his titers of DCB compared to all the other students in his class. The systematic error could have resulted from Diego continually rinsing his what? Pipette with water before each use. Now remember, your pipette needs to be rinsed of your allocate, which is vitamin C. Normally your pipette is rinsed with your vitamin C. But because you're like rinsing it with water, you're diluting the concentration. So you're decreasing your titers. So yeah, that will decrease your results. We want higher results. So we want higher results. So that will decrease it. If you use a if you rinse it with water, you're decreasing the concentration. So you would use basically less. You'll have a lower titers, not higher titers. So that wouldn't be correct. Pipettes with DCB solution before each use. No, and remember we said pipettes use you should be using vitamin C. You don't use the titrant. So if you're using the titrant, think about it. If you're using the titrant, what happens? So if you're using the titrant, so pipette. So if it already has DCB, and if you're putting some, the pipette has vitamin C. When you put vitamin C, it would have already reacted. Some of it would have been already reacted, which is a problem. So that would decrease the titers again, because already some of it has already reacted. So that wouldn't make. So it would have decreased. You would have had lower titers. Pipettes with vitamin C solution before. No. Remember, wait, that's not going to have any effect because remember, pipettes are normally supposed to be rinsed with vitamin C. So in this case, which is our allocate. So yeah, that wouldn't have any effect. So C is wrong. D, conical. So it has to be D, but conical flask with vitamin C shouldn't before each use. So remember, your conical flask is basically rinsed with water. And so if you're rinsing it with vitamin C, you're actually adding that extra vitamin C. The concentration has increased, so hence your titers will increase. So it has to be D. But that's correct. 29, 4 students recorded data for each experiment as shown in the table below. We have Ben, Chang, Oliver, and Ravinder. Here's the average. The true value expected for this titration was this. Which student was able to obtain a more precise data? Remember, precision is, what is precision? It's basically how close are those values together? How close are the range? Are they very closely related, those values? And so that's what we want to calculate. Now, this, if you do physics, you are in luck. Very in luck. I mean, in the chemistry books, I haven't actually seen them doing these kind of questions. Like, they give you these points and they're like, which one's the most precise data? There is a formula to know which one has the most precision. It's basically this. You want the low number, which is we want the lowest number where basically you want to take the max minus your min. What do we mean? This is precision. This is the formula for precision. So basically, the lower the number, the more precise the data is. So the range. So for example, look at Ben here. What is the highest value he got? It's this one, 16.2. And what's the lowest value he got? It's that 15.9. So remember, so we got the max and we got the min. Now minus them. So what's 16.2 minus 15.9? That is 0.3. That's actually good. So that's low. Now we have to do it for Chang, Oliver, and Ravienda and see which one has the lowest. And the one that have the lowest means that they actually have a very more precise because the ranges are very closely related with each other. So what about this one here? So this is the lowest. This is the highest. Let's try to check the other ones too. So this one's the highest. And this one's the lowest. This one's the highest. This one's the lowest. Yep, that's the lowest. So let's do the same. So let's do Chang first. That's 0.5. I can just see that 0.5. The other one is 0.6. If I'm not, yeah, 0.6. Yep. The other one is 7. I think 1.3. Let me just double check. 1.3. Beautiful. Now, which one has the lowest range? You can see it's at 0.3. So Ben has a more precise. So Ben's more precise. Remember, when you're calculating precision, it's how close, how related are those values? Are they, in terms of range, are they closely related to each other? Be careful of the word, what do we call average? So that average is used to calculate how accurate are those data points. So yeah, so that's that one. Last question, 30. Do you plot data generated during an experiment in which she measured the volume of gas being formed over a period of time? Which of the following plots shows a non-linear relation as well as clear evidence of systematic error present? All right, so it's non-linear relationship because we don't want it like a line. A line is linear. You can see this is a line. I'm not going to lie, this is a line, so that's wrong. This one looks good. It's like a curve, so it could be that one. Also, that one also looks like a curve. And D looks like a line. So these are two linear, so take those off. So it'll only be B and C. Now, when we're talking about systematic error, remember, this is what systematic error looks like. So if I draw a graph. So systematic error are basically when points are uniform, but are wrong. So for example, so let's use this green graph to be like the correct values. See, these points here are all correct. They're on lying on that true value. So that green here is your true value. True value. What basically like systematic error is, it's basically still uniform. You see the points lie perfectly on the line, but are, they are wrong. And normally systematic error occurs because like fluctuating, something's wrong with your, what do we call it? Equipment. It's normally equipment. And this is your systematic error. You can see this is a systematic error. You can see how they're uniform. They look related to the true value, but remember, each of these are you can see how it's uniform, and the increments are always the same for each. So imagine this was the true value. It's increased by this much increment. So it's this true value. It's increment to this true value. This value, it's increased by this. Can you hear these cats just fighting? I can hear my cats. Oh my god, these cats are fighting outside. So yeah, so you can see how the systematic error is uniform. So it looks like that. Which one of the following is uniform? Well, looking at these here, B, you can see that B is, this is like nice, but then it fluctuates, a little bit fluctuating. See how it's fluctuating with you? So it kind of looks like it has random error, and it needs to be nicely uniform. Whereas C actually looks uniform. You can see how it's uniform. Like if you draw a line, it nicely passes through all those points. Whereas if you draw this one over here, if you draw a line in this, B, let me just drop this out. You have this more roughness. It's not more compared to, you have to like move to the sides to get these points. Like look at that point. That point's out of the range. So yeah, in comparison, I would say C would be the most. It's more smoother. The more smoothness, look how smooth it is compared to that one. I mean, look at these data points, yeah. Data points are much more. So if I draw like a nice line like that. So if am I able to pass, it's like able to pass most through all of them. This one over here would be like, so if it's not really, come on. Why is it really making my life hard if I just curve it? Wow, really? It's really something like that. And if I push it right for every point, you can see that, yes, it's passing through every point, but this rubbish point does not lie on it. So it's kind of, this little bit passes, but this is out of it. It's like a random error. So also this one, but it's much more, like you can see that these points are much more closely related compared to this. So I would say C is more systematic. And it's a little bit it's not confusing. You can see visually they are correct. Like for example, look at these two, perfect. So I would say, absolutely. C looks most nicest in terms of a uniform. Done. I hope you guys enjoyed the video. Please make sure to like and subscribe for more future videos like this. I should be able to try to finish those short answer in some time. I do have uni, so absolutely. I have so much uni work. But I hope you guys enjoyed this video. Please take care of yourself and good luck with your studies. Have a great day.